afternoon, everyone. So, I welcome you all for the problem solving session 11 for the NPTEL course Computational Fluid Dynamics. And this course is instructed by Professor Sreenivas from the Department of Chemical Engineering, IIT Madras. And the live session is handled by myself, Kartika, a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So we have been having these live sessions every Saturday from 3 p.m. to 5 p.m. So this is like we are almost into the towards the end of the course, and we'll have today's session as well from 3 p.m. We will see the course layout shortly. So since it is a 12 weeks course, we have introduction to the calculation of flow in a rectangular duct in week 1, and week 2 we have seen about the calculation of fully developed flow in a triangular duct. It is derivations of equations governing fluid flow, and week 4 it is equations for incompressible flow and boundary conditions, and week 5 it is basic concepts of CFD, finite difference approximations. Week 6 it is basic concepts of CFD, consistency, stability and convergence. So in half of the session what we have seen is that what is CFD, where it is applicable. Like in flow computational fluid dynamics, what we are studying is that we are trying to understand what happens in the system through computational methodologies. And for that, what we generally do is we define the geometry, we discretize the geometry into small meshes, and we do the calculations in each of those small mesh regions. So for that there are different approaches for discretization. We have finite difference method, finite volume method and finite element method as well. And again in calculations also there are so many methods to get the solutions. So in the first few weeks it is about calculation of flow in a rectangular duct using the finite difference method, and second week it is calculation of fully developed flow in a triangular duct using finite volume method, because these two are the basics and we are trying to understand what we do in CFD by having a very basic problem. And week 3 it is derivations of equations governing fluid flow. So what we do is in CFD we are solving for the equations using the we are solving for the equations using and getting the solutions. Like we have continuity equation, we have momentum conservation equations when we are dealing with basic computer fluid flow problems. So we solve for the pressure, velocity, those variables, and for that we need to know the equations. So as I mentioned, it is continuity equations and 3 momentum balance equations in each directions for problems concerning only fluid flow. If there are additional heat transfer involved in the system, we need to solve for those as well. And in week 4, equations for incompressible flow and boundary conditions. When we talk about solving, we need to know certain values in the system for us to get a proper solution. Like in fluid flow through a circular pipe, we are giving some inlet velocity. So those are all the boundary conditions which we are specifying, and it can be velocity inlet, pressure outlet, and those sort of conditions. And week 5 it is basic concepts of safety, finite difference approximations, wherein we use the Taylor series approximation to get our finite difference methodologies, and we saw about the different order, different schemes, and how each scheme was giving better result, or when to use which. And later on, it doesn't mean that when we have a problem after we are discretizing that we will get the solution. So we need to have few concepts like consistency, stability, and convergence. Lack's theorem also states that when we have a consistent and stable system, we will get the converged solution. And week 7, it is about solution of Navier-Stokes equation for compressible flows, wherein we are concerned about the system where density was varying. Since density was varying, it was present inside the computer equation, so it was not a matter. We can solve those. So basically, since density was inside the system of equations, there was a bit easier to get the solutions. Whereas when we are talking about the solution of Navier-Stokes equations for incompressible flows, density was not varying, so we take density as constant from the continuity equation. So in continuity equation in the compressible flows, density will be present. Uh, Also, it will be present in the momentum conservation equations. Whereas in the system for incompressible flows, it will be absent in the continuity equation but present in the momentum conservation equation. So it becomes an issue. So for the compressible flow systems, we had various methodologies like McCormick scheme, beam-warming scheme, etc. to get the solution. Whereas when we come to incompressible flow systems, we have these issues which I mentioned. So we used things like pressure artificial compressibility method, in which we are introducing an additional term and getting solutions similar to the compressible flow systems. And the second one was stream function vorticity method, wherein we reduce the equation and return it in a different form using the stream function and the vorticity variables. And other methods include pressure two other methods are also there. And later on, week 9 and 10, what we were doing is that we were getting the solution of linear algebraic methods using the basic methods and advanced methods. In basic methods, we saw about Gauss seidel, Gauss linear, I mean, and Jacobi method, those things. Whereas in advanced methods, we have seen about that is in last class, we have seen about successive over relaxation and how it was better than Gauss-Seidel cases. And also we saw about things like alternating direction implicit method and Stone's semi-implicit procedure. So those are all the various methods that we have seen. It would be helpful to know that there are so many methods that were given and which made the solution of COD easier in today's world. So that is the case, and in today's class, that is in week 11, we will be seeing about the basics of finite volume method, including grid generation, how structured unstructured measures are there, and what are all the uses. So those things we will be seeing. And lastly, in 12th week, it will be about turbulent flows and turbulence modeling, which we will see in next class. So books and references, we have 5 books. First one is Ferziger and Perick M. Computational Methods for Fluid Dynamics, Berlin, Springer, Berlin, Germany. And second one, it is Hirsch, Numerical Computation of Internal and External Flows, and John Wiley and Sons, New York, USA. And see Batankar SB 1980, Numerical Heat Transfer and Fluid Flow, Hemisphere, Washington DC. And fourth one, it is Verstig, HK and Malal Sekara, and Introduction to Computational Fluid Dynamics, the Finite Volume Method. And last one, it is Anderson JD's Computational Fluid Dynamics, Basics with Applications. So yeah, today's session is on mesh generation, like finite volume method and mesh generation. So we will see that. Okay, so in today's class, basically we have 3 figures, A, B and C. So since it is about mesh generation, we are having A, B and C, 3 meshes we are having, and we need to get the solutions for the problems coming. So just for your quick reference, what is happening is that 3 different geometries are there. And here it is about almost like we have some thing, and here it is different, and here it is different. Here we are having triangulated things, and here it is like small rectangular elements. And more than that, here we can give some points to each, but here it is kind of not possible. So we will see what these meshes are in detail in the coming slides. First question is that with reference to figure 1, which of the grids can be considered as a structured grid? With reference to figure 1, which of the grids can be considered as structured grids? So we will see the options first. Option 1 figure 1a, option 2 figure 1b, and option 3 figure 1c, and okay, uh, 1, 2 and 3 are not options, like they are sub options, we can say. A 1 and 2, B 2 and 3, C 1 and 3, D 1, 2 and 3. Basically 1 is 1A, 2 is 1B, 3 is 1C. So before I give out the answer, if any one of you is willing to give an answer, that would be good. Okay, alright, we'll see the answer. It is so the answer is option C, that is 1 and 3. So if we go and look back at the figure, A, B and C, that is this is 1, this is 2, this is 3. So in A we are having some structured form. So from here if we can see that we are giving I, if we take it in x direction, we will be giving I equal to 1, 2, 3, 4, 5. So some form of structure we are able to give. Whereas in 2, if we say I equal to 1, I equal to 2 in the x direction, we are not very sure which I we are talking about. That is I equal to 0 here, 1 it can be here or here. Again 2 it can be here, here or anywhere. Like we cannot give a structured way. So this one is a structured mesh. This one is an unstructured grid. Whereas coming back here, we will again have it as a structured grid only. That is I equal to 1, I equal to 2, I equal to 3. We will be able to give out certain numbers based on the grids, and we will get this representation easily. So that is why A is structured grid, B is unstructured grid, C is again structured grid. So answer is A and C, that is 1 and 3. 1 is 1A, 2 is 1B, 3 is 1C. So 1A and 1C are structured grids, 1B is an unstructured grid. So the right answer is option C, 1 and 3. So again, if we look back, we are having two sample structured grids and this one is an unstructured mesh. So in structured mesh, we were able to see that I equal to 1, I equal to 2, I equal to 3. If we divide it like that, we will be able to give certain numbers based on that, which is not possible in case of unstructured mesh. Here itself, if we are seeing, as I mentioned, like we are not able to give out certain indices in these regions particularly. These regions again it is unstructured. These regions again it is unstructured. So that is why it is called an unstructured grid. Similarly, if we apply this concept to our question, we will be able to see the relevance there also. So that is why 1A and 1C are structured grids and 1B is unstructured grids. So a structured grid means that the volume elements are well ordered and a simple scheme like IJK indices can be used to label elements and identify neighbors. A structured grid means that the volume elements are well ordered and a simple scheme can be used to label elements and identify neighbors. So here we are able to see a well-ordered volume elements, mesh elements, and a simple scheme. Example is IGK indices. I1 I mentioned, right? I equal to 1, I equal to 2, I equal to 3. Y similarly J is equal to 1, J is equal to 2, J is equal to 3. That simple scheme can be used to label elements and identify its neighbors. It need not be I equal to 1. So or x is equal to x plus delta x, I times delta x. So some form of structure we will be having, that is what is given over here in structured grid. Whereas in unstructured grids, volume elements can be joined in any manner and special lists must be kept to identify neighboring elements. So here we are ordering and arranging the neighboring elements in some way, whereas in unstructured grids, volume elements cannot be joined easily, and but I mean it can be joined easily for ease of generation will be there, but it will be difficult to arrange them in certain order. We cannot arrange them in certain order, and we need special lists to keep identifying the neighboring elements. Similarly, in our question with reference to this particular figure, we are able to give a certain ordering in the x direction and y direction. If we keep it in this way, we are able to see that order in figure 1a and 1c, whereas in 1b we are not able to identify that order. So 1b is unstructured grid and a and c are structured grid. So that is the answer. So answer is 1 and 3. Option C is the right answer. So a structured grid means that the volume elements are well ordered and a simple scheme can be used to label elements and identify neighbors. In unstructured grids, volume elements can be joined in any manner and special lists must be kept to identify neighboring elements. So that is the thing. Now we will see few more examples. So this is a sphere, alright, and here we are able to see a structured mesh arrangement. Like we are able to see ordered volume elements, but what issue we will face is that near the vertex and all, right, it is like, okay, this is not a sphere, this is kind of a circle, like two-dimensional thing. So here we are able to see skewed cells. So these skewed cells will give like kind of issues while we are getting the solutions. So that may be avoided when we use the unstructured mesh, which kind of looks like this. So the same what we call same geometry, it can be done using structured mesh and unstructured mesh as well. Similar example is given in this two figure. Here the same square geometry, we are able to use it in structured mesh and we are able to use it in unstructured mesh as well. Like the mesh generation can be structured or unstructured. Here those things are same, like same circle geometry and same square geometry, but we are able to do it via both the methods, that is structured meshing or unstructured meshing. So that is the case with question 1. So now we are clear with the concept of what is structured mesh and what is unstructured mesh. So now we will go to question 2. In question 2, what is asked? For the solution of Navier-Stokes equation in irregular geometries, which of the following grids can be used? For the solution of Navier-Stokes equation in irregular geometries, which of the following geometries can be used? First one, it is Cartesian grids. Second one, it is structured grids. Third one, it is unstructured grids. So when we are talking about irregular geometry, it can be anything, right? Like uh, it 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 won't be a simple geometry anymore. So when we are talking about the irregular geometry, we need to consider certain aspects as well, and in those cases it will not, or it is not always promising to go with the regular Cartesian grids, Cartesian geometry and Cartesian gridding. It won't be effective to go with that always. So first one is false, like we cannot go with the Cartesian grid system. And second one, it is structured mesh. Structured grid, we can get it from irregular geometries as well, provided we know the concept of meshing very well. Like when you do meshing, there are various tools available. One is like in ANSYS itself, you have ANSYS meshing and ICM meshing as well. So when we are talking about going with the default thing, right, it will go with the unstructured mesh, and calculation will be a bit difficult over there, but you will have a certain hang on getting an refined mesh in all regions. When irregular geometry are our domain of interest, we cannot always get it using a proper thing, like Cartesian grid is impossible as I mentioned, and the next one is structured grids and unstructured grids. In structured grids you will get the grading, but it will be a bit tricky, and you need to know in which angle you need to mesh to get the proper structure meshing. It is not always impossible, but you need to know, or you need to have a lot of practice to get it done. So that is the problem with structured grids. Whereas in unstructured grids, what you can do is you can get it easily for irregular geometries. So 2 and 3 are possible. So when we talk about the solution options, we have option A 1 and 2, option B 2 and 3, option C 1, 2 and 3, option D only 3. So we have 2 and 3 as the right answer. So option B is the right answer. For the solution of Navier-Stokes equations in the irregular geometries, which of the following grids can be used? We can use structured grid or we can use unstructured grid as well. So 2 and 3 is the right answer. Option B is the right answer. So we have structured grids and unstructured grids as well. So answer is option B is the right answer, where we have both 2 and 3. Option B is the right answer. Now we will have question 3. Which of the following can be claimed as an advantage of an unstructured grid method of solution over a structured grid solution? So basically, when we have both the grids, why do we prefer one over the other in certain places? So what is the advantage of unstructured grid over structured grid? So one thing is you can generate the mesh easily in using unstructured grid, which is not possible using structured grid. So we will see the options listed over here. First one is ease of grid generation, and second one it is ease of grid refinement, and third one it is ease of solution of discretized equations. So we are given three things. First one is ease of grid generation, second one is ease of grid refinement, and third one is ease of solution of discretized equations. So we are talking about advantages of unstructured grid method over a structured grid solution. So we know that it is easier to generate unstructured grids than structured grids. So first one is true, ease of grid generation. Second one, it is given that ease of grid refinement. Again, grid refinement in certain zones you can achieve it using unstructured mesh, which is not possible directly using structured mesh. And third one, it is ease of solution of discretized equations. Ease of solution of discretized equations. But when we talk about unstructured grid and unstructured grid, if we have the same kind of geometry for both the cases, we will get the solution with better thing in structured grid than unstructured grid. So therefore we cannot say that solution will be easier obtained using unstructured grid. If that is the case, we can go with all geometrical problems using unstructured grid only, because it is having certain advantages as well as disadvantages, especially in terms of these things like solution getting solution is difficult in unstructured grids, and getting meshes easier in unstructured grids. So 1 and 2 are true, whereas third one is false. So option A 1 and 2, option B 2 and 3, option C 1, 2 and 3, option D only 3. Again we have 4 options. If we look at it, we know that 1 and 2 are right, so which is given in option A, that is 1 and 2. Which of the following can be claimed as an advantage of an unstructured grid method of solution over a structured grid solution? So the answer is option A, that is 1 and 2, ease of grid generation and ease of grid refinement. So answer is option A, 1 and 2. So we'll quickly see how option A is the right answer, and we will see what are all the advantages of unstructured grid solution. The grid density can be controlled in any region without worrying much about the density getting increased in another region. So this is one advantage of an unstructured grid. For example, this is our domain. This is our structured mesh, okay, or we can keep it like this as well. When we are talking about mesh refinement in this particular zone alone, what we will do, we will divide it into further. But since this is a structured mesh, the division will be carried over entire thing. it will be carried over entire thing, and we will not get the solution. Like, I mean, here it will be refined, here it will be refined as well. So the grid density in the whole domain will be affected. Whereas this is the case of unstructured mesh. You are refining here alone, the density will increase here without it getting affected in this region. So that is the advantage of unstructured mesh. The grid density can be controlled in any region without worrying much about the density getting increased in another region. Second one, the ease to use with complex geometries. Unstructured mesh can be used with complex geometries which cannot be done using simple structured meshes. So can be computed within an hour. Like, getting unstructured mesh is actually easier, but getting solution from unstructured mesh is not easier. So that is the issue. Easy to use with complex geometries, we can mesh it in an hour and be computed within an hour. And lastly, it is, we don't have to worry much about skewness or bad quality, since the grid generation algorithm itself take care of that most of the time. So we are in the circular mesh itself, we have seen that the chances of skewness was high in case of structured mesh, whereas in unstructured mesh that issue was not there. We need not worry about that because the algorithm itself takes care of those things. We don't have to much worry about the skewness or bad quality of the mesh, since the grid generation algorithm takes care of that most of the time. So that is the advantages of unstructured grid solution. So we'll now see question 4. In question 4, what is given? Which of the following statements is not true when we use a structured grid for flow through complex geometry? Which of the following statements is not true when we use a structured grid for flow through a complex geometry? Options are, first one, body fitted grids can be used only in two dimensions. Body fitted grids can be used only in two dimensions. Second one, finite difference method techniques cannot be used. Finite difference techniques cannot be used. And third one, diagonal dominance condition of the coefficient matrix is preserved. So we have three statements. First one is body fitted grids cannot be used, and second one is finite difference techniques cannot be used, and third one it is diagonal dominance condition cannot of the coefficient matrix is preserved. And we need to identify which of the statements is false, is not true when we use a structured grid for flow through a complex geometry. So first one, it is, we are talking about a complex geometry and we are applying structured grids and we are getting the solution. So first one, it is given that body fitted grids can be used only two-dimensional problems. So this is false. We can use body fitted grids for three-dimensional problem as well. It is a type of structured grids for they are like we use them with boundaries of complex shapes. It will fit by mapping the physical domain into the computational domain with a simpler shape. And second one is finite difference techniques cannot be used. So the finite difference technique cannot be used is also a false statement. We can use finite difference method. In fact, it is much preferred for using with the finite structured grid method. Like for structured grid method, using finite difference method is way easier. And third one, it is diagonal dominance condition of the coefficient matrix is preserved. This can be true under certain conditions, but not always true. Because like it is often preserved in structured grids, but it depends on specific formulation and discretization which we are using, so we cannot generalize the statement. So all three are not false to be said. 1, 2 and 3 are false statements. So we'll look at the options and we will get back to the solution. First one, it is option A, only 3, and second one, it is B, 1 and 2, and C, it is 2 and 3, and D, it is 1, 2 and 3. So which of the following statements is false? So answer is, from our understanding, all three are false. So option 1, 2 and 3 is the right answer. So all three are actually false statements. So option is, answer is option D. 1, 2 and 3. Option D, 1, 2 and 3 is the right answer. We will quickly see why that is the case. Well, the first statement given was body fitted grids can be used only for two-dimensional problems. So we agreed upon it that it is a false statement. Body fitted grids can be used for two-dimensional or three-dimensional problems. This statement is not true. Body fitted grids, which are a type of structured curvilinear grid, can be used for both two-dimensional and three-dimensional problems. They are designed to fit the boundaries of the complex shapes by mapping the physical domain into a computational domain with a simpler shape. So body fitted grids can be used only for two-dimensional problems. The statement is false. Body fitted grids, which are a type of structured curvilinear grid, can be used for both two-dimensional and three-dimensional geometries. They are designed to fit the boundaries of a complex shape by mapping the physical domain into a computational domain with a simpler shape. And second one, statement was finite difference technique cannot be used. Again, it is a false statement. This statement is not true. Finite difference techniques can indeed be used with the structured grids. In fact, structured grids are often preferred for finite difference methods because they provide a regular connectivity that simplifies the implementation of these methods. So, as I mentioned, finite difference can be used with the structured grid, and moreover, it is preferred for finite difference method to go with the structured grids because they provide a regular connectivity that simplifies the implementation of these methods. And the third statement is diagonal dominance condition of the matrix is preserved. The diagonal dominance condition of the coefficient matrix is preserved, and this statement can be true under certain conditions, but it is not universally applicable. Diagonal dominance is often preserved in structured grids due to the regular structure, which can lead to matrix with diagonal entries that are larger than the sum of diagonal entries. However, this depends on specific formulation and discretization used. So this statement is not true always. So it can be true, it cannot be true, which we cannot generalize actually. So diagonal dominance condition, what do we mean by diagonal dominance condition? Wherein the diagonal element is larger in size than the sum of the off diagonal elements. But it can be preserved in certain conditions because we are using the structured grid. The probability is high, but again we cannot generalize. The diagonal dominance is often preserved in structured grids due to the regular structure, which can lead to matrices with diagonal entries that are larger than the sum of the off diagonal entries. However, this depends on the specific formulation and discretization used. So all three statements are false under some way or the other. So answer is actually option D, 1, 2 and 3 is the right answer. That is, we are asked to identify the false statements or which of the following statements is not true. So all three statements are false. So 1, 2 and 3 is the right answer. So now we will go to question 5.
Which of the statements is true about the transformation of the Laplace equation into a non-orthogonal curvilinear coordinate system? Which of the following statements is true about the transformation of the Laplace equation into a non-orthogonal curvilinear coordinate system? So now we are asked to identify which statements is true when we are transforming the Laplace equation into a non-orthogonal curvilinear coordinate system. So first one, it is the elliptic equation remains elliptic, and second one, elliptic equation becomes parabolic, and third one, elliptic equation becomes hyperbolic, and last one, parabolic equation remains parabolic. So first thing is, when we are talking about the Laplace equation, it is an elliptic equation. And the second thing is, when we are transforming, we are doing the transformation, there is no change in the nature of the equation. So if it is an elliptic equation, it remains elliptic. If it is a parabolic equation, it remains parabolic. But the system of equation under our concern when we are talking about Laplace equation is that the system of equations are elliptic equations. So elliptic equation remains elliptic is the right answer. So first one is the right answer. First one, option A 1, option B 2, option C 3, option D 4. So which of the following statements is true about the transformation of the Laplace equation into non-orthogonal curvilinear coordinate system? It is that the elliptic equation remains elliptic is the right answer. So actually answer is option A. A1 is the right answer. So quick answer to this. Elliptic equation remains elliptic. When transforming the Laplace equation into a non-orthogonal curvilinear coordinate system, the nature of the equation is preserved. The elliptic nature of the equation is preserved. The Laplace equation is elliptic in its standard form in Cartesian coordinates, and even after the transformation into a curvilinear coordinate system, it remains elliptic. This is because the transformation doesn't change the fundamental nature of the equation, but instead it only affects the form of the equation in the new coordinates. When transforming the Laplace equation into a non-orthogonal curvilinear system, the elliptic nature of the equation is preserved. The Laplace equation is elliptic in its standard form, which we have seen in few classes before as well. So it remains the same even after the transformation into a curvilinear coordinate system. This is because the transformation does not change the fundamental nature of the equation, but rather it only affects the form of the equation in the new coordinates. The second option given was elliptic equation becomes parabolic. This is not true statement. The Laplace equation remains elliptic even when transformed into curvilinear coordinates. Again, the third statement given was elliptic equation becomes hyperbolic. This is also not true either because the Laplace equation remains elliptic after transformation. And finally, the parabolic equation remains parabolic. So this is not relevant in case of Laplace equation because the nature of Laplace equation is it is elliptic, it is not parabolic. So only the first statement is true. Elliptic equation remains elliptic because when we are doing the transformation into a non-orthogonal curvilinear coordinate system, the elliptic nature of the equation is preserved. The Laplace equation is elliptic in its standard form, and even after the transformation into a curvilinear coordinate system, it remains elliptic because transformation does not change the fundamental nature of the equation, but instead it only affects the form of the equation in the new coordinates. So that is it for question 5. Before moving to next question, we have a problem statement. So the coming up problems will be based on this statement. So we will see it carefully. Again, it will be mostly about meshing and different types of meshes as well. So first is that we have a sample triangulation of a semicircular 2D domain. So we have a two-dimensional domain and it is a semicircular domain, and we are doing triangulation of it and sample triangulation of a semicircular two-dimensional domain. So this is our domain. So this is our problem statement. More to say, this is our figure of interest. The coming up questions will be based on the figure. this figure. So question 6, what it is asking is that for the case shown in figure 11.1, that is a semicircular domain figure, which of the following statements is true? First one, it is a structured grid. I repeat, first one, it is a structured grid. Second one, it is an unstructured grid. And third one, it is structured grid can also be used. And fourth one, unstructured grid can also be used. For the case shown in figure 11.1, which of the following statements is true? First one, it is a structured grid. Second one, it is an unstructured grid. And third one, structured grid can also be used. And fourth one, unstructured grid can also be used. So when we go back to our domain, our question in concern, we can clearly see that it is not a structured grid. We cannot give straight out any indices, or we cannot list it using any special schemes, or it cannot be joined in some ordered manner as well. It is joined in an mixed random fashion, so it is not a structured mesh. It is an unstructured mesh. But can we use structured grid for this? Yeah, yes, we can use the structured grid because we have seen a circular mesh example in the first problem as well. Like we have seen one example where we use the structured mesh. So if I go back, this is our structured domain. If we divide it, we will get the unstructured domain. Sorry, this is our circular domain. If we divide it, we will get this semicircular domain. So here we are using structured mesh for circular domain, and we are also using unstructured mesh for circular domain. So as it is possible to get a structured mesh for it as well. So the answer is actually, it is an unstructured mesh, but we can use structured grids as well. So that is the answer. It is an unstructured grid, but we can use structured grid as well. So 2 and 3 is the right answer. We will see the options first. Option A, it is 1. Option B, it is 2. Option C, it is 1 and 4. Option D, it is 2 and 3. So we know that it is an unstructured grid, but we can use structured grid as well. This week's assignment problems are more or less based on these sample problems. So listen carefully before, so you will be having no issues when we are submitting the assignments. So answer is option D, that is 2 and 3 is the right answer. Now we will go to next question. That is question 7. Again we have the same figure 11.1, two-dimensional semicircular domain. Given Dirichlet boundary condition along the curved side and Newman boundary condition along the diagonal of the domain shown in 11.1. So what are we doing? We are given the Dirichlet boundary condition along the curved side. Curved side we are giving Dirichlet boundary condition,
And Newman boundary condition we are giving along the diagonal of the domain. So this is our diagonal, this is the Dirichlet boundary condition, this is Newman boundary condition. So what do we do in Dirichlet boundary condition? In Dirichlet boundary condition we specify the value to the variable, whereas in Newman boundary condition we specify the value to the derivative of the variable. So uh, we are asked that how many algebraic equations need to be solved simultaneously when solving a steady state scalar transport equation over the domain. So we are solving steady state scalar transport equation over the domain, and we need to identify how many algebraic equations we need to solve simultaneously. First one, it is 42 plus or minus 2, and second one, it is 32 plus or minus 2, and option C, it is fewer than 27, option D, more than 45. So we are given Newman boundary condition along the diagonal of the domain, and we are given Dirichlet boundary condition along this. So we will just first count the number of equations, number of meshes, internal meshes. So it is 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28 29 30 31 32 33 34 35 36 37 38 39 40 41 42. So we have 42 triangular elements, and so in this is using finite volume method. So we are using the cell centers for getting the values. So we will be solving approximately 42 equations, and it can be plus or minus 2, 42 plus or minus 2, because we have 42 triangular elements. The number of equations to be solved simultaneously is 42 plus or minus 2. So option A is the right answer. Answer is option A, that is 42 plus or minus 2 is the right answer. So we counted the number of triangles, and it is closer to 42 plus or minus 2. So we will have to solve those many equations. Now that is for question 7. Now we will see question 8 actually. Before that, we will take a small break, and we will come back by 3:54. We will come back by 3:59 something. We will start it then. Alright, we'll start now. There is some network issues from my end, so that's why I'm not sharing my video. But apart from that, if you have any delays, let me know. Let this meet is sharing your screen be there. Otherwise, I may not know if it. We have seen about question 7. The number of algebraic equations which we need to solve simultaneously when solving a linear steady scalar transport equation over the domain. So it is 42 plus or minus 2. Now so question 8 it is, which of the following statements is true about the solution scheme shown in figure 11.1? Which of the following statements is true about the solution scheme shown in figure 11.1? First one, it is local grid refinement is possible. Second one, local grid coarsening is possible. Third one, multi-grid approach is possible. So first one, it is, which of the following statements is true about the solution scheme shown in figure 11.1? So it is like local grid refinement is possible, and second one, local grid coarsening is possible. So the one which we have seen in figure 11.1 is an unstructured mesh. So what do we know about unstructured mesh? We can do local grid coarsening or we can do local grid refinement as well. We have seen that doing mesh variation in one side, mesh controlling in one side will not affect the mesh density in the other region. So that is the advantage of unstructured mesh. So similarly, which of the following statements is true about the solution scheme in figure 11.1? It is that we can do local grid refinement, it is possible. We can do local grid coarsening, again it is possible. Third one, multi-grid approach, again multi-grid approach is possible. Why? Because what is multi-grid approach? We will be using a series of meshes wherein we will solve a series of error reductions in each of those grids, and we will get the solution finally by going back to the initial mesh. So that is the multi-grid approach which we have seen in the last class. So are we able to use it for figure 11.1? Yes, we will be using it. We can use it for figure 11.1 as well. That is, multi-grid approach is possible. So local grid coarsening is possible, local grid refinement is possible, and we can use multi-grid approach as well. So all three statements are in fact true. So we will see the options. Option A, it is 1 and 2. Option B, it is 2 and 3. Option C, it is 1 and 3. Option D, it is 1, 2 and 3. So since 1, 2 and 3 are true, the right answer is option D, that is 1, 2 and 3. Local grid refinement is possible, local grid coarsening is possible, and multi-grid approach is possible as well. So option D is the right answer, that is 1, 2 and 3. So that is for question 8. Now we will see question 9. Question 9 states that which of the following statements is true about the solution of the linearized algebraic equations resulting from the discretization of a steady scalar transport over the domain shown in figure 11.1. Which of the following statements is true about the solution of linearized algebraic equations resulting from the discretization of a steady scalar transport equation over the domain shown in figure 11.1. So, we will see the options. First one, SOR method can be used. Second one, alternating direction, implicit ADA. Third one, LU decomposition method can be used. And the fourth one, it is, okay, we don't have fourth one. We have three options. SOR method can be used, and second one, alternating direction implicit can be used, and third one, LU decomposition method can be used. So we are having a semicircular domain, and we need to identify which of the following is true about the solution of the linearized algebraic equations resulting from the discretization of the steady scalar transport over the domain shown in figure 11.1. So the first one, SOR method can be used, successive over relaxation methods, wherein we use the optimization parameter and get the solution. That method can be used. That is a true statement. Second one, ADI, that is alternating direction implicit method can be used. So we have seen that ADI takes advantage of the tridiagonal matrix algorithm in their algorithm. So if we see that, is it true? When we use ADI method, we will get the solution easily. Whether we will get solution by implementing this method, it is a question, because we cannot promise a tridiagonal matrix algorithm in this particular problem. We will not get the tridiagonal matrix algorithm, so ADA scheme is impossible here in this question under our consideration. And third one, LU decomposition method can be used. This is true statement because it is a normal method, basic method, and which we can use in any problem. So LU decomposition method can be used. So 1 and 3 is the right answer. So given the options, we have option A 1 and 2, option B 2 and 3, option C 1 and 3, option D 1, 2 and 3. So which of the following statements is true about the solution of the linearized algebraic equations resulting from the discretization of a steady scalar transport equation over the domain shown in figure 11.1. So first one, SOR method can be used. It is true. second one is false, and third one is true. So answer is option C, that is 1 and 3 is the right answer. So 1 and 3 statement is the right statement, and it is given from option C. So we will quickly see why that is the case. Finite volume approach is used to solve for the system in the unstructured grid solution. So our mesh under consideration is a finite volume method. So successive over relaxation and LU decomposition methods can be used to solve the system, whereas alternating direction implicit method, ADA method, requires the condition for the tridiagonal matrix algorithm, TDMA algorithm, to be met. Therefore we cannot use ADI advanced alternating direction implicit method for this system. In ADA, what we do, we have two set of equations. In one we keep one part of the equation one in the one direction implicit and the rest explicit and solve. Similarly, we keep other directions implicit in one equations and solve the system as well. So now moving to question 10. What we have in question 10, we have it that the transformation of an unsteady scalar transport equation into non-orthogonal curvilinear coordinate system lead to the following consequences. So in the similar to the first problem wherein we transformed the Laplace equation into non-orthogonal curvilinear coordinate system, and we found that the elliptic equation remains elliptic, the nature of the equation is preserved. So similarly, we have an unsteady scalar transport equation which we are transforming into non-orthogonal curvilinear coordinate system, and we need to identify its consequences. First one, mathematical nature changes from hyperbolic to parabolic, and second one, cross derivative terms disappear. And okay, we have two statements only. The first one, it is mathematical nature changes from hyperbolic to parabolic, and second one, cross derivatives term and disappear. So we are asked to identify true statement, that is which is the true consequence. First one, the mathematical nature changes from hyperbolic to parabolic, which we know it as false. So first statement is false because we have seen that we are not changing the mathematical nature of the system, rather we are only concerned with things. Similarly, cross derivative terms disappear is also a false statement because cross derivative terms do not disappear. So we will see the explanation in the next slide, but before that both the statements are false statements, so that is the case. So options statements 1 and 2 both are wrong. The transformation of an unsteady scalar transport equation into non-orthogonal curvilinear coordinate system lead to each of the following consequences. First one, mathematical nature changes from hyperbolic to parabolic is false. Similarly, cross derivative terms disappear is false. So first one, option A, it is 1. Option B, it is 2. Option C, it is both 1 and 2. Option D, it is neither 1 nor 2. So the right answer is actually both are false. So neither 1 nor 2 is the consequence. So option D is the right answer. So we will see why. In question 10 it is given that
mathematical nature changes from hyperbolic to parabolic? So we will see why it is false. Generally, the transformation into curvilinear coordinates does not inherently change the mathematical nature of the equation from hyperbolic equation. The type of equation, hyperbolic, parabolic or elliptic, is determined by its original form and the physical processes it describes, such as advection, diffusion or both. However, the transformation can introduce additional terms due to the curvature and non-orthogonality of the coordinates, which might affect the numerical stability or complexity of the solving the equation but not its fundamental type. So what happens in the transformation into curvilinear coordinate system? It does not change the mathematical nature of the equation. It introduces additional terms. It can introduce additional terms due to the curvature and non-orthogonality of the coordinates, which might affect the numerical stability or the complexity of solving the equations, but not its fundamental nature of the equation. So second one, cross derivative terms disappear. Again, this is a false statement. Cross derivative terms do not necessarily disappear when transforming into non-orthogonal curvilinear coordinates. In fact, non-orthogonal curvilinear coordinates often introduce additional terms due to Christoffel symbols, which arise from the non-orthogonality and curvature of the coordinates and the metric transform tensor components. These terms can include cross derivatives, making the transformed systems appear potentially more complex than their Cartesian counterparts. So this is the case when we are doing the transformation. Both the statements are false statements, therefore the answer was neither 1 nor 2 is the right answer. Now we will go to question 11. Question 11, it is given that which of the following statements can be claimed as the advantage of an unstructured grid method of a solution over a structured grid solution. First one, ease of tackling irregular geometries. Ease of tackling irregular geometries. Second one, ease of solution of Ax is equal to B after discretization. Third one, ease of grid refinement after solution. Okay, we have three statements and we need to identify which of the following can be claimed as an advantage of unstructured grid method of solution over a structured grid. So first one, it is given that ease of tackling irregular geometries, which is true. We can use unstructured grids easily in irregular geometries than implementing structured grid. Second one, ease of solution of Ax is equal to B after discretization. This is false because we cannot get solution easily from the unstructured mesh. We can get solution easily from the structured grids, whereas we cannot get solution easily from the unstructured grids. So second statement is false. Third one, ease of grid refinement after solution. So again we know that when we are using unstructured grid, ease of grid refinement is easier when we use the unstructured grids. So third statement is also true statement. So 1 and 3 are right statements. Second one is a false statement. So 1 and 3 are the advantages of using unstructured grids over the structured grids. So answer is 1 and 3. We will see which of the options are aligning with our answers. So the first one is option A 1 and 2, option B 1 and 3, option C 2 and 3, option D 1, 2 and 3, option A 1 and 2, option B 1 and 3, option C 2 and 3, option D 1, 2 and 3. So which of the following can be claimed as advantages of an unstructured grid method of a solution over a structured grid solution? So 1 and 3 is the right answer. Option B is the right answer. Actually, I'll insert page number. Without it, it is a bit difficult for me. sorry, not date and time, slide number output of right. So answer is option B. Oh, sorry, not B. Yeah, B is the answer. 1 and 3 is the right statement. So now we are going to question 12. In question 12, what is asked? Consistent evaluation of fluxes in the finite volume method means dash. Option 1, at least second order accuracy in evaluation of fluxes. Third, second one, evaluation of fluxes at midpoint of phases. Third one, okay, we have only two statements. So what do we mean by consistent evaluation of fluxes in the finite volume method? At least second order accuracy in evaluation of fluxes, this is false because we are not assuring anything. It is not mandatory for consistent evaluation. Similarly, evaluation of fluxes at midpoints of phases is not related to the consistent evaluation of fluxes in the finite volume method. So both the statements are false. So we'll look at the options. Option A 1, option B 2, option C both 1 and 2, option D neither 1 nor 2. So answer is option D, that is neither 1 nor 2 is the right answer. So we will look at its explanation. At least a second order accuracy in evaluation of fluxes is not mandatory for consistency. Consistency in finite volume method refers to accurately approximating the integral form of the governing equations, which can be achieved even with first order accuracy. Higher order accuracy improves precision, but it is not inherently tied to consistency. So question under our consideration is related to consistency, which is not related to second order accuracy. So first one is false statement. Similarly, evaluation of fluxes at midpoint of phases is not strict requirement for consistency. While fluxes are often evaluated at phases midpoint using interpolation or reconstruction schemes, this is a numerical choice and not a defining aspect of consistency. Although we do it out of a numerical choice, we are not doing it as a defining aspect of, we are not using it as a defining aspect of consistency. So third one, the defining aspect of consistent flux evaluation in FVM, that is finite volume method, is flux conservation. What we are doing with consistent flux evaluation, what do we mean by that? It is flux conservation across the common phases of adjacent cells. So that is not given over any of the two statements, so it is a false. Consistent flux evaluation in FVM means that flux conservation across the common phases of adjacent cells. So now we will go to question 13. In question 13, what is given? Which of the following statements is false about Bowyer-Watson algorithm for Delaunay triangulation? What is the following? Which of the following statements is false for Bowyer-Watson algorithm for Delaunay triangulation? So answer is, we'll look at the options first. All the boundary grid nodes are inserted first. Second one, all the nodes are inserted randomly. And third one, fewer number of triangles are produced than in the advancing front method. So we are given three statements and we are asked to identify which of the following statements is false when we are using Bowyer-Watson algorithm for Delaunay triangulation schemes. So out of the three statements, we need to identify which of them is false. So we will see the questions. All the boundary grid nodes are inserted first. So this is in fact a false statement. So first statement is false. In the second statement, it is given that all the nodes are inserted randomly. In Bowyer-Watson algorithm, we insert all nodes randomly. So second statement is true statement. Coming to the third one, it is fewer number of triangles are produced than in the advancing front method. So this is again false because we cannot say anything about the number of triangles produced in the Bowyer-Watson algorithm when compared to the for Delaunay triangulation scheme.
So 1 and 3 is 3 are false, whereas the second one is true. So we will see the options. Option A, it is 1. Option B, it is 2. Option C, it is 1 and 3. Option D, it is 2 and 3. So as per our understanding, first and third statements are false statements. So option D is the right answer. So option D is the not option D, sorry, option C, 1 and 3. So it is in option C. Option C is the right answer. Now we will see why second statement is true and the rest of the statements are false. So thing is, all boundary grid nodes are inserted first. That is what is given in first statement. All the boundary grid nodes are inserted first. Though this statement is not necessarily true, the Bowyer-Watson algorithm typically starts with an initial super triangle that encloses all the points to be triangulated. So initial super triangle that encloses all points to be triangulated. Points are then inserted one at a time, but there is no requirement that the boundary nodes be inserted first. So we are not following any pattern that boundary nodes we are inserting first, then we are going in the inside. So this is not true. So first statement is a false statement. The algorithm can handle points in any order, although it often starts with the super triangle to ensure all points are closed. Second one, all nodes are inserted randomly. So from here, the first statement itself, we have understood that there is no requirement that the boundary nodes be inserted first, and it can handle any points in any order. So it is insertion at a random rate. The algorithm can handle points in any order. Algorithm works by adding points one at a time to the existing triangulation regardless of their orders. So last one, fewer number of triangles are produced than in the advancing front method. So again, this statement is generally not true. Number of triangles produced by the Bowyer-Watson algorithm is determined by the Delaunay criteria, which maximizes the minimum angle of all triangles. The advancing front method, on the other hand, can produce a variable number of triangles depending on how the front is advanced and the criteria used for triangle creation. There is no inherent guarantee that the Bowyer-Watson algorithm will produce fewer triangles than the advancing front method. This is generally not true. It may or may not produce. Mostly the triangulation criteria is that Delaunay criteria, which minimizes the minimum angle in all the triangles. The advancing front method produces a variable number of triangles depending on how the front is advanced and the criteria used for triangle creation. So there is no inherent guarantee this method will produce less number of triangles than the advancing front method. So that is why all nodes are inserted randomly is only true statement and the rest are all false statements which we have identified correctly. So coming to question 14, we have that the following possibility cannot happen during the advancing front method of triangulation. Following possibility cannot happen during the advancing front method of triangulation. First one, triangles of high aspect ratio are created. Second one, domain outside the boundary is partly included during triangulation near concave boundaries. Third one, domain outside the boundary is partly included during triangulation near convex boundaries. So we are asked to find which of the possibilities cannot happen during advancing front method of triangulation. So first one is that cannot happen. So triangles of high aspect ratio are created. So this statement is true. It can happen when we are using the advancing front method of triangulation. This can happen. Whereas the second statement, domain outside the boundary is partly included during triangulation near concave boundaries is false, and similarly, sorry. Yeah, it is false and it cannot happen. So, and similarly, third one, domain outside the boundary is partly included during triangulation within the near the convex boundaries. So this is also false and it cannot happen as well. So in the question it is asked which of the following possibility cannot happen during the advanced front method of triangulation. So since it is about which cannot happen, 2 and 3 are the right answer. So option A 1, option B 2, option C 1 and 3, option D 2 and 3. So as per our understanding, second and third is the impossible things. So answer is option D. 2 and 3 is the right answer. Option D is the right answer. Okay, we will see why first can happen and the two others cannot happen. First, when triangles of high aspect ratio are created. So this can happen, especially if the algorithm does not properly optimize the triangle quality. The advancing preferred method can produce high quality triangles, but it may not always guarantee optimal aspect ratios. So optimal aspect ratio is not guaranteed. So triangles of higher aspect ratio can be created, especially when we are doing complex geometries or mesh size varies very significantly. We can go or we can get high aspect ratio triangles. So this is a possibility that can happen. And second one, domain outside the boundary is partly included during triangulation near concave boundaries. So this is false statement. This is a potential issue with some triangulation methods, but the advancing front method is specifically designed to avoid including areas outside the boundaries. It starts with the boundary edges and advances inward, ensuring that the triangulation remains within the boundaries methods. So, this can happen in certain boundary triangulation methods, but advanced fronting method is specially designed to avoid including areas outside the boundaries for concave or convex boundaries. It starts with the boundary edges and advances inward, so that the triangulation remains within the boundaries. Last one, domain outside the boundary is partly included during triangulation near convex boundaries. Again, it is false. This is less likely to happen with advancing front method, as it is designed to maintain boundary integrity. This method starts from the boundary and progresses inward, which helps prevent the inclusion of external areas even near the convex boundaries. So that is with advanced front method. We will go to question 15. In question 15, what is asked is that following possibility cannot happen during Bovai-Watson method of integration. And first one, domain outside the boundary is partly included during triangulation near concave boundaries. And second one, domain outside the boundary is partly included during triangulation near convex boundaries. So option A, it is 1. Option B, it is 2. Option C, both 1 and 2. Option D, it is neither 1 nor 2. So now we are again back to talking about Bovey-Watson method of triangulation, and it is given, two statements are given. First one is Bovey-Watson method triangulation includes domain outside the boundaries near, includes domain outside the boundary partly near the concave boundaries and near convex boundaries. So thing is, for concave boundaries, uh, it can include, but in convex boundaries it cannot include domain outside the boundary partially. So in concave boundaries the possibility is there slightly, but in convex domain it cannot happen.
So the answer is it cannot happen in convex boundaries. Bowyer-Watson method of triangulation cannot include the domain outside the boundary partly during triangulation near convex boundary. So second statement is the right answer. Option B is the right answer. So why domain outside the boundary is partly included during triangulation near concave boundaries? So this can happen in case of concave boundaries because of the way the triangular Delaunay criteria works. So when Bowyer-Watson method is used, it can include domain um, near the concave boundaries. Because of the way it works, if a point is near the concave region, so it can include, right? In convex it cannot mostly. Near a concave region, the triangulation might spill over into regions outside the domain. If it is like this, imagine. So if we are using triangulation criteria, sometimes it can spill over into the outside boundary, and if boundary is not strictly enforced during the triangulation process, the possibility is there actually to include the domain outside the boundary for the concave boundaries. Whereas for the convex boundaries, it cannot happen because for convex boundaries, the Delaunay criteria generally ensures that the triangles are often contained within the convex domain. The Bowyer-Watson method typically ensures that the triangles formed near convex boundaries do not extend outside, as the boundary points themselves will tend to keep the triangulation contained within the convex shape. So Bowyer-Watson method ensures that the uh, domain outside the boundary is not included when we are going with the convex boundaries. Domain outside the boundary is partly included during triangulation near concave boundaries. So this is a potential issue with some triangular mesh with some triangulation methods, but the Bowyer-Watson method typically starts with a super triangle that encloses all points that defines the triangulation. However, if the algorithm is not properly implemented, if there are numerical errors, it might still occur, particularly near concave boundaries where super triangles removal can leave gaps. Domain outside the boundary is less likely, is partly included during triangulation near convex boundaries. This is less likely to happen with the Bowyer-Watson algorithm as it is designed to maintain boundary integrity. It starts from boundary and progresses inwards, which helps prevent the inclusion of external areas even near the convex boundaries. So second statement is less likely to happen. It cannot happen. So therefore second statement was the right answer, because in the question it was asked which cannot happen. So second one was the right answer. So yeah. Now we have a last question for today's session. Question 16, what is asked? Which of the following increases when the grid size is decreased? So when we are decreasing grid size, uh, what does it mean? We are increasing the number of grid points. The number of grid points is increased, grid size is decreased. So why do we go with grid size reduction, and which of the following increases when grid size is decreased? So first one, it is truncation error. Second one, asymptotic convergence rate. So in the question, what is asked? In the question it is asked which of the following increases when grid size is decreased. When grid size is decreased, the grid size actually, like how much information it can pass across that distance. If distance is small, grid size is small, truncation error actually decreases. If you remember what we call truncation error, delta x to the power of n, depending on the order of accuracy or those things. But if delta x is small, delta has x has become small, the overall truncation error will also become small. So when delta x grid size decreases, truncation error also decreases. Second one, asymptotic convergence rate. When grid size is decreased, the convergence rate also decreases actually. So second is also false. Options given are option A 1, option B 2, option C 1 and 2, option D neither 1 nor 2. So the answer for our question is option D, neither 1 nor 2 is the right answer. The question 6 answer is that when the grid size is decreased, that is the number of grid points increases. Both are the same. When you are increasing grid size, you are increasing the number of grid points. The following changes occur. Truncation errors. Truncation errors generally decrease as the grid size is decreased. Truncation errors arise from approximating derivatives or integrals using finite differences or other discretization methods. By increasing the number of grid points, the approximation becomes most accurate, reducing the truncation error. Truncation error generally decreases as the grid size is decreased, and it arises from approximating derivatives or integrals using finite differences or other discretization methods. When you are increasing the number of grid points, approximation becomes more accurate. So obviously the error will reduce. So option 1 is false. Second one, asymptotic convergence rate. So asymptotic convergence rate is a property of the numerical method itself and does not inherently increase or decrease with grid size. However, as the grid size decreases, the solution typically approaches the asymptotic range of convergence more closely, where the theoretical order of convergence is more accurately reflected. The convergent rate itself remains constant but is more reliably observed as the grid becomes finer. So we are not sure uh, about it as well. Therefore, neither 1 nor 2 increases when grid size is decreased. Instead, truncation error decreases with increase in grid size and the observed convergent rate becomes more consistent. I am sorry I mentioned it as it will decrease, but it does not decrease, but it becomes more consistent with the theoretical rate as the grid becomes finer. Because what is asymptotic convergence rate? It is a property of the numerical method itself and does not inherently increase or decrease with the grid size. But as the grid size reduces, the solution typically approaches the asymptotic range of convergence more closely, where the theoretical order of convergence is more accurately reflected, and convergent rate itself becomes constant but is more reliably observed as the grid becomes finer. So first one and second one both are false statements. Yeah. So yeah, that's it for today's class. This is the last problem. So if you have any doubts, you can ask. So basically, to give you a recap of what we have seen in today's class, we have seen about the structured meshes and unstructured meshes in today's class, and how it is and what are all the advantages and disadvantages of both the methods, and when do we prefer one method over the other, and what are the things we have seen about certain triangulation algorithms as well. One is like Bowyer-Watson algorithm and advancing friend method, and what are all the things that happen in each of those triangulation methods also we have seen in today's class. So it is just to give you an idea of finite volume method and also including aspects on grid generation. So most of the things we have covered. The applications will be on different meshes, different structured domains, geometries. But questions from the assignment I have seen, and it is more or less likely to be similar to what we have seen in today's class. So if you have seen and understood today's class, it will be easier for you to submit your assignments on time, and you will get answers for assignments. If you have any other doubts in today's class or previous classes, you can ask me, and these recordings will be made available to you people, and also the PPTs will be available to you.
So if you have any doubts, you can clarify it at later stage as well. So next week we will have one more class on week 12 problems, and later on that we will have one more session wherein we will have cover all the things, like it will be a summary of what are all the things we have seen from week 1 to week 12. That is, next week will be week 12, and we will be covering one summary session with all the problems from week 1 to week 12. All the problems in the sense, all the concepts related things which will help you and give you a quick recap before you appear for the exam by the month end. So that's it from my end. If you have any doubts, you can contact me later as well. Yeah. If anything is left out, I don't think so. But yeah. I'm just seeing if there is anything left out. Also, we have seen about the transformation, and we have seen that nature of the equation remains constant. It does not change during transformation. More or less, that's it in today's class. I think we have almost covered what are all the things that we require. Evaluation of fluxes. Consistent evaluation fluxes in finite volume method means conservation across the common phases of adjacent cells. So yeah, that's it for today's class. We will close this session now, although we have some time. We have no doubts, and we have seen the recap as well. We'll close today's sessions. We will meet again next week at the same time, 3 p.m. And if you have any doubts from today's class as well, you can ask next week, and from any previous classes, if you have doubts, you can ask that as well. I am closing the session for today. Thank you for attending, and we will meet again next week. Thank you.